Okay, good morning, everybody. It's a great pleasure to introduce Tim Palmer from University of Oxford, Department of Physics. And I want to read you, to introduce him, a small paragraph. Tim Palmer did his PhD in general relativity in the 70s at the University of Oxford under Dennis Sciama and Roger Penrose, but turned down a postdoc opportunity to work with Stephen Hawking, not least because of a growing skepticism about quantum mechanics as a fundamental theory of physics. Instead, he pivoted to a career in climate physics, in which he made a wide range of theoretical and practical contributions on the nonlinear dynamics and predictability of weather and climate. As a result, Tim was elected a Fellow of the Royal Society and an international member of the US National Academy of Sciences. Among many prizes around the world, he has won the Dirac Gold Medal of the Institute of Physics and a gold medal from the Royal Astronomy Society. And in 2010, Tim moved back to Oxford as a Royal Society research professor. And in recent years, I think we witnessed this, he has focused on addressing the reason he changed fields in 1977. If not quantum mechanics, then what? I think you will tell us then what today.
Thank you.
Thank you, Tim.
Thank you, Kozlov. Well, it's a pleasure to be here and to give this talk. Let me start with a slide showing something maybe many of you have contributed to this, but a survey that Nature did on the quantum foundation's preferred explanation of quantum mechanics. And it basically shows a very large number of different opinions. Still perhaps the most popular being Copenhagen, but maybe people who opted for that weren't necessarily all that confident in their answer. So I think it's fair to say, 100 years after the birth of quantum mechanics, we're still no nearer to a consensus understanding of quantum mechanics. And what I want to do is propose something which I suppose is a little radical. I'm not going to try to make an argument for why, Copenhagen is to be preferred over Bohm, or Everett is to be preferred over cubism, or whatever it is. I don't think that actually gets to the heart of the problem. I think the heart of the problem is more to do with the axiomatic nature of quantum mechanics, and maybe that we have been misled for almost a century, actually, about one of the most primitive axioms of quantum mechanics. And this is the one, I guess, was formalized by von Neumann in the early 30s, which is that we describe the state of a quantum system as some kind of vector in a complete Hilbert space, vector space H over complex numbers. And then the state is evolved with the Schrödinger equation. Now, I put the word complete in red, because that, in a sense, it's that single word which is the emphasis or the focus of my talk. A complete space to a mathematician is one where the limit points of all sequences, Cauchy sequences and things, are contained in the space. And in my view, that really is the problem. And it's kind of ironic in a way. It's less that maybe quantum mechanics is incomplete, which is the standard sort of EPR conclusion, and maybe more the conclusion it's somehow too complete in a very specific sense, which I'll talk about. Yeah, so my claim is von Neumann's axiom is too liberal, and it's basically that which makes quantum mechanics incomprehensible. I guess it was my view when I changed fields that if you really can't understand a theory, trying to marry it with a different theory is always going to be difficult. So I think a good first step to, for example, trying to synthesize quantum and gravitational physics is at least to have a theory of quantum physics that you understand or is comprehensible. Anyway, so what I'm going to try to do, this is my contribution to this debate, if you like, that was instigated by the Nature survey. My contribution is to look at, in a sense, tightening the axiom up. And by tightening the axiom up, I'm going to mean moving from this notion of a continuum state space, a continuum vector space, to something which is much more inherently discretized. And I'll say exactly what I mean by this probably in the next slide. But I'm going to kind of claim in my talk that it really, once you do that, once you make that move, it really opens up a lot of things which are hitherto been quite either difficult or impossible. I would say something that it uncovers, which has always been quite difficult, is the information-theoretic basis for the wave function. I'll talk about that. I'm going to claim it also provides novel conceptual understanding of the violation of Bell inequalities without the need for non-locality in the strict EPR Bell sense of the word non-locality. I'll talk about that. And that it provides a novel solution to the measurement problem. So I imagine these are three of the most important outstanding problems in quantum foundations. So now, I've given this talk from time to time, for example, in Oxford in physics, my own departments of physics, and the physicists sort of typically, I don't know, shrug their shoulders and say, well, yeah, this is all very well, but give me an experiment we can do that will prove, you know, your idea about discretized Hilbert space is correct. And this has kind of been bugging me for a long time, but I've kind of come round to a possible experiment which could be potentially performed on a quantum computer in not too many years. And I hope if I can get through the talk, I'll get to that point, because that's kind of been for me an important point where I can kind of make contact with physics and say, look, here's a potentially testable idea. So I'm going to call this rational, for want of a better word, rational quantum mechanics, and just to avoid confusing with Rovelli's relational quantum mechanics, which I don't particularly see. Well, there may be connections, but it's not entirely obvious. I'll put a little a there to stand for rational. All right, so the basic idea is actually extremely sort of straightforward in a sense, and it can be illustrated by just starting with a single qubit. So we write that down in some basis, the 1 minus 1 basis, and there's an amplitude, cos theta over 2 or sine theta over 2, and a phase, a complex phase phi. And, you know, in quantum mechanics, that's evolved with the Schrödinger equation. That's the second part of the von Neumann axiom set. So I'm going to continue with that process. I'm not proposing to modify the Schrödinger equation. I'm not adding any terms onto the Schrödinger equation or anything like that. However, the crucial point is in saying what bases are allowable or allowed bases. What are the bases in which this state is defined, mathematically defined? And I'm going to say, this is the kind of guts of it, if you like, and it generalizes very straightforwardly for multiple qubits, but just to say a basis of the state is only defined in a basis 1 minus 1 if the state in that basis has an amplitude such that if you square it, its square is a rational number of the form m over L. So L is an integer, m is a whole number, so it goes from 0 to L inclusive, and that's so L is a variable in this theory, and I will talk a lot about what the numerical value of L is. But just for the time being, think of it as a very, 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 very large number. We'll see it's roughly 10 to the power 100 for a typical qubit in a quantum computer. But anyway, it's a very, very, very large number. But it is rational, and that's the key point. So from elementary trigonometry, 2 cos squared theta over 2 minus 1 is cos theta. So cos theta is a rational number. But the phase now, the second part of the discretization, is the basis is only mathematically defined if the phase in degrees, or the phase as a fraction of 2 pi, is another rational number of the form n over L. And again, n is another whole number between 0 and L. Yeah. Yeah, well, that's what I'm saying is not correct. This is the whole point. Exactly. So normally we think of the Schrödinger equation as sort of basis independent, and that of course is consistent with the von Neumann thing about a complete vector space, and that's what I'm kind of focusing attention on. That's correct. Yeah. Sorry? An experiment, by definition, will always have the right basis. But L is. But we'll come to an experiment. Just trust me. We'll get to an experiment where this will test this. Just if we get too many questions, the talk will go on too long. So let me just give the talk, because a lot of things you might want to ask, I'll cover. So unless it's really, really mega specific, I suggest we leave it to the end. So an important point, conceptual point here, is that if I do some analysis, and I'll show you some analysis that we will do, for example, with Bell, where we end up having to consider bases where these amplitudes, squared amplitudes or phases, turn out to be irrational numbers, then according to this sort of ansatz, we'll say that this is in this model of the world, this is the state is undefined. Okay. So let's now the little piece of mathematics. It's very elementary number theory, but it absolutely underpins everything I'm going to talk about. And I'm going to call it, well, it's sometimes called in the literature Niven's theorem. It's like one of these things. Maybe Niven wasn't the first person to prove it, but he has a very nice little book on irrational numbers, where there are lots of interesting number theoretic properties of, for example, trigonometric functions. So what I'm calling Niven's theorem says that if phi is a rational multiple of 2 pi, or phi is rational in degrees, then the cosine of that angle phi is irrational, except at a very, very, very small number of exceptions. So when cos phi equals 0, plus or minus a half, or plus or minus 1, so in degrees we're at 0, 60, 90, 120, 180. So what that means is if you kind of give me, let's say at random, a phi, if you give it to me in degrees, 36.7892134 something degrees, I can tell you from Niven's here that number is irrational. The cosine of that angle is going to be irrational. And a corollary of Niven's theorem, which I won't bother to prove, but it's very simple. It comes from the cosine formula for spherical triangles, but this will turn out to be important for Bell's theorem, is that if you have a triangle on the unit sphere, spherical triangle, so the distance between the vertices you can think of as in terms of angles. So theta BC is the angular distance between B and C on this unit sphere. And then you've got an internal angle phi. So if phi is rational, in other words, phi over 2 pi is a rational number, and it's not one of these exceptional values, then the theorem is that the cosine of the angular distance of the 3 sides. So if you take the cosine of the angular distance of each of the 3 sides of the triangle, not all 3 of them can be rational. So 2 of them could be rational. If 2 of them were rational, then the third one is certainly irrational. So the impossible triangle is where all 3 of them are irrational. The cosines are irrational. The impossible triangle is where the cosines of all three angular distances are rational. We'll come to that, back to that in a few minutes. I should say perhaps you might be having, if you're mathematically inclined, you might be getting a little bit uncomfortable with this idea of having irrational numbers as being undefined and rational numbers being defined. And you might say, well, what's the mathematical basis for that? And I'm going to come to that point in a few minutes. But I want to kind of motivate the importance of this with a very simple example. And I kind of see this as like a warm-up for Bell's theorem. And that's just a Mach-Zehnder interferometer. Now, as we all know, in Bell's theorem, a crucial question is whether experimenters have free will. They can freely choose their measurement settings. And in this model, they certainly can freely choose. And the free choices are, in this particular setup, the experimenter has two free choices. The first free choice is whether to keep in place the second half silvered mirror at the top right. So in the top diagram it's there, and in the bottom diagram it's not there. So he or she is either chosen to leave it there or take it out. And the other free choice they have is to determine the relative length of the two arms of the interferometer. Now, for this particular experiment, we'll say it doesn't actually, nothing matters, but just for focus, we'll suppose that the experimenter chooses for them to have equal lengths. Now, the thing about quantum mechanics is if you analyze, so basically the top one we're doing a kind of an interferometric measurement, and in the bottom one we're just basically measuring which way the particle went around the interferometer. It's kind of, one is a like particle measurement, the other is a wave measurement. Now, the form of the wave function in quantum mechanics is that phi enters the Hilbert vector when you're doing an interferometric measurement through one of the amplitudes, and for the particle measurement, you do a kind of unitary transform which takes the phase to takes the angle phi, the phase angle to a complex phase. So just keep those two equations in mind when we come to the next slide. Now, a really important point in all of this is that experimenters are free to choose their experimental parameters, but when they do so, they do it with some nominal degree of accuracy or some nominal degree of precision. So if we suppose the nominal value of phi is 0, which means phi is approximately 0, let's say it's plus or minus 1, it can be as small as you like, 1/1000th of a second of arc from 0, okay? I don't care actually what, you can give me any experimental tolerance you like, but it must be something. Let's say it's 1/1000th of 1 second of arc. Then I can say for all phi consistent with that phi nominal of 0, phi and cosine of phi are simultaneously rational only when phi equals 0 precisely. And that's what Niven's theorem says. If you remember, there was one exception at phi equals 0, but it has to be equal 0 precisely. If it was like a gazillionth of a degree different from 0, phi and cosine phi would be, one would be rational. If one was rational, then the other would be irrational. Well, as we'll see, this parameter or variable L will be an exceptionally large number. So we've got typically, let's say, 10 to the 100 possible values, exact values of L that are consistent with that nominal value of 0. In all but one of the 10 to the 100, phi and cosine phi are not simultaneously rational. Just to go back to this slide, just recall, if you do the interferometric measurement, you require cosine squared phi over 2 to be rational in this model. And if you do the which way, you require phi itself to be rational. And what we're saying is that it's basically impossible for those two to be simultaneously rational. And you would translate that into like a more physical language to say that it's impossible for the quantum state to be simultaneously defined in both. Of course, that's exactly what we mean by complementarity. So we kind of have a picture of complementarity just coming from number theory, nothing more than that in a sense, once you do this discretization of Hilbert space. Now, what I'm claiming here is, this is an important point, that the experimenters are free to choose their nominal settings, but they don't have any choice. They're not free to choose whether cosine phi is rational or irrational. That's set by the laws of physics. And of course, they're not free. In the real world, they're not free. No experimenter would say that they were free to set exactly what the experimental settings are, because, for example, a gravitational wave from some distant astrophysical black hole collision might suddenly pass through the interferometer just as they're taking the measurement. So it's very important in this model to distinguish between nominal settings, which this becomes critical for the Bell theorem. It's important to distinguish between nominal settings where the experimenter is free to choose and exact settings where they're not free to choose. Okay, now I do want to just spend a few minutes, I hope I'll get to this point in the talk, which may seem a little bit esoteric if you're a physicist, but just trust me, if you're a mathematician, what I'm about to say is absolute bread and butter, especially if you're a number theorist. Because I want to just address this question, which I'm sure you must have some visceral kind of sense of. Does it make sense really to kind of reject irrational numbers somehow? Allow rational numbers but reject irrational numbers? Because irrational numbers, after all, can be like infinitesimally close to rational numbers. So what sense does that mean I'm discussing here something incredibly fine-tuned? Or so this is really an important point to just conceptually clarify. I want to do it without getting too bogged down in technical detail here, but if you were asked a mathematician what you mean by an irrational number, they would say it's a Cauchy sequence of rational numbers, or it's the limit, or they might say it is the Cauchy sequence, or it's the limit of the Cauchy sequence of rational numbers with respect to the Euclidean metric. And that last bit is really important. Because we've known for 120, 30 years or something, there is a completely different metric. Interestingly, there's only one other metric. There's not a whole family of them. There's one other metric with respect to which the rationals can be completed. So one can define a completely different class of Cauchy sequences of rationals which have different limit points defined by this second metric. It's called the p-adic metric. And the important point is that with respect to the p-adic metric, irrational reals are just undefined. It's not that they're far away or they just they're not undefined. So the rationals are defined, but the irrationals are undefined with respect to the p-adic metric. The reason I personally got interested in p-adic numbers originally was because of links to chaos theory, which I've done a lot of work on over the years, because p-adic metrics are to fractal geometry. Fractals underpin chaotic systems typically, as the Euclidean metric is to Euclidean geometry. So if you have a Cantor set, I'll hopefully get to that later, you can do arithmetic analysis, you can even do calculus on Cantor sets, providing you formulate everything with p-adic numbers, or two-adic numbers in this case. We'll come to this again a little bit later. But I just want to, that's a kind of a conceptual point that might help. So it does make mathematical sense to sort of say if something is turns out, as we'll see now, irrational, it makes sense to say this is now mathematically undefined. All right, so with that as background, I want to come to Bell theorem. I guess we all would agree that there are basically three assumptions, something to do with realism, something to do with locality, and then this third assumption, which is goes by different names, but often called measurement independence, which says if you have a hidden variable theory, then the probability of a given lambda hidden variable being realized is independent of, so capital A and capital B denote the measurement settings. So I realize my notation might not be completely standard here, but capital A and capital B are measurement settings of Alice and Bob. And people typically tend to be scornful or dismissive about attempts to question that assumption because it's seen as synonymous with the free choice, experimenters having free choice. And I think as Anton said, if experimenters aren't free to choose their settings, then then what's the point of doing science, sort of thing? It undermines the whole scientific endeavor. All right, so I'm not going to question that, don't disagree with that at all. But what I do want to emphasize here is this distinction between nominal and exact settings. And again, we will assume that Alice and Bob are free to choose their measurement settings, but only in this nominal sense, to some sort of level of accuracy. And we'll see that this rationality constraint, which is kind of a modest one, I would say, because you can in this. So everything I will say in this part of the talk, L can be absolutely as large as you like. So from an experimental point of view, it can be utterly, the discretization could be so fine, it just is utterly undetectable. Okay, but as long as L is not infinite, that's the only thing I would say, then we will find that this measurement independence assumption will be violated for exact settings. Okay. It's easier to describe this with the Bell 64, because I can then refer to this impossible triangle corollary that I mentioned earlier. CHSH is just a little bit more complicated, but it doesn't add anything different. So just bear with me if I go through this with the original Bell 64. So that's the inequality. C is a correlation, and the correlation in quantum mechanics is given by the cosine of the relative angle, or the scalar product between the two measurement settings of Alice and Bob. And again, we're going to assume they're freely chosen. This is a kind of real world thing, so we are talking necessarily about nominal settings. So what I want to do is talk the way I see it anyway, talk it through from a kind of experimental perspective. That's my first part here, one. And then I want to talk it through from a theoretical perspective. Okay, now from an experimental perspective, what we would do, of course, is calculate these. There are three correlation functions in this inequality, in the Bell 64 inequality. So what we would do is we would calculate the three correlations from three separate sub-ensembles of particles, particle pairs, entangled particle pairs. So just get your head into gear, we'll suppose we do the first one on Monday, second one on Tuesday, and the third one on Wednesday. And then after Wednesday, we can put the results together and see whether the inequality is violated or not. And we know, of course, it is violated for suitable choices of nominal measurement settings. Now, the point of this theory is to say there are these exact settings which underpin the actual experimental settings. So if we take Monday, they had the same, each run of the sub-ensemble on Monday had the same nominal settings. But of course, gravitational waves pass by and the exact settings will vary from one run to the other. But according to the theory, we require that for each individual run, we don't know, of course, what the exact settings are, but we'll assume the theory is correct, and it will then say for each individual run, the exact setting A dot B must be, remember that's cosine, so that must be a rational number. Of course, the exact A and B will vary from one run to the next on Monday, but they'll all be consistent with the nominal setting. Okay, so that's fine, there's nothing, we just assume the theory can do that, so that's all good. And then Tuesday comes along, we do the second experiment, and the theory says, well, within the second sub-ensemble, it now is the case that the exact setting A dot C is rational, the scalar product. And the Wednesday setting, the third sub-ensemble, each run must have B dot C as rational. So that's let's say all good. That's fine. But now what I want to do is look at it from the theoretical point of view. How would you derive Bell's theorem within the context of some kind of hidden variable model? So in other words, where does this measurement independence assumption come in? Whoops. And yeah. And so what we do is we actually take, so we assume we have some functional relationship between, oh. Here's an experiment. This is what an experimenter would do. They would have three ensembles. And now I want to say, well, I'm about to explain that, hopefully. Yeah. Okay. Well, at this stage, random. Right. Well, if you'll bear with me, I'll make the point. Okay. This is why it's perhaps best to leave discussion to the end, because then you can see whether I've said it or not. Well, just bear with me, and you can tell me whether I've introduced something randomly or not. So if you want to derive Bell's theorem, you theoretically, from a hidden variable model, you integrate or you sum this product of spin functions, exactly the same as in the inequality, over lambda. Now, this is the point, and this is where it relates to the Mark-Zender interferometer, that when you actually do an experiment with one lambda, or with one individual run, there is one real-world situation, let's say it's a Monday, where you're measuring in the real world A and B, but for these other two products of spin S, A and C and B and C, these are necessarily counterfactual for that given lambda. So two of these products are obtained from counterfactual measurement bases. Now, so this is the point, that by Niven's theorem, let's say we're on Monday, so we know A and B, because that was, for a Monday run, A and B corresponded to the real world. That cosine of theta AB is rational. We know from mathematics, from number theory and spherical geometry, spherical trigonometry, I should say, theta BC and theta AC cannot be simultaneously rational. So it's impossible for the three cosines to be simultaneously rational. Hence, the singlet state, that Bell state, can't be defined in both of the two additional counterfactual bases. It's defined in the real world basis A and B, but not in A and C or B and C. Or for Tuesday, it might be A and C is the real world, then A and B and C are counterfactual. Or on Wednesday, B and C was the real world, A and C are counterfactual. The singlet Bell state can't be defined in both counterfactual bases. So in my model of discretized Hilbert space, this is the point, I cannot derive the Bell inequality. I cannot prove the Bell inequality because I cannot integrate that quantity over lambda, because I can define two of the products, but I can't define the third. It's a property of spherical trigonometry. Well, when you say I violate Bell inequalities experimentally, for sure.
Now you say it's a counterfactual and so on. I understand your story, but I said, no, but a counterfactual means just that I use this apparatus along this direction to my precision. I will call this, by definition, A, no matter whether I'm measuring it with B or I'm measuring it with C. Then I can derive Bell inequality.
Right. But I have to assume that it makes sense that the states are well defined along those counterfactual directions. Well, all right. let me say, let me, let, you derive it. I mean, you just go through the standard derivation that Bell did in his paper. You have this quantity which you sum over lambda, and you fiddle around with the terms, and you get the inequality. And what I'm saying is, let me just read this out, because I'm not the first person to say this. So this is interesting, because I think the first person to say it was Henry Stapp back in 71. The third way out is to deny that the measurements that could have been performed but were not would have had definite results had they been performed. Anton, in his book on the dance of the photons, there is a third assumption. It is the assumption, that's why Oshie was here, so we could discuss this point. There is a third assumption. It is the assumption that it makes sense to consider what kind of experimental results would have been obtained if one had measured a different property than the one that was actually measured. And an important, this is philosopher Michael Redhead, makes the point, it was precisely in relation to that top equation. He says in his book, a very important point to notice here is that the possessed values of spin in Bell's inequality are in general counterfactually possessed. Now, no, well, don't call it classical. I don't want to call what I'm talking about classical, but it is deterministic, and it is because it's based on, for example, it's based on these p-adic numbers, so it's not classical. So don't call it classical, right? It's not classical. I will talk. I'm trying to understand where Bell's. I don't want to get into too much depth here because I'll run out of time. Well, you're shrugging your shoulders at me. I'm trying to describe a model of physics which has the properties of being realistic and actually EPR Bell local, but is not classical, because it has this property that for the exact measurement settings, because of these trigonometric constraints, one cannot derive Bell inequalities, all right? So I'm taking the analysis that Bell did and saying this is where it fails. It fails because of counterfactual definiteness, because of the exact settings. Now, it's not classical because of that. We'll come on to that very shortly. Okay, what I'm saying is no weird stuff is needed, right? We don't need non-locality. We don't need the fact that Bob's measurement outcome depends on Alice's measurement setting, what she had for breakfast. That's what I call weird stuff. It doesn't depend on the world being unreal. That's weird. It doesn't depend on retrocausality. That, in my view, is weird. It doesn't require free will to be violated. That's what I would call weird. It doesn't require some kind of conspiracy. It doesn't require worlds to split and recombine. I call that weird. It doesn't require wormholes. I call that weird. Superdeterminism, fine-tuning. So that's my point. Nothing weird here. Okay? Yeah. Because when you're tossing a coin, you are not exploiting this the fineness of the discretization of Hilbert space does not play a role. And in fact, in general, this is what I want to do. I want to come to an experiment where it does play a role. If I don't. No, we're talking about, as I say, numbers here like 10 to the 100. So how do you get to testing a number to one part in 10 to the 100? I will show you how to do that in a minute. yeah, because with I'll explain, because this theory includes the classical limit, and these properties would not appear in the classical limit. But you have to just bear with me for a few minutes, and we'll get there. Okay. I want to say kind of why I will come on to that in a few seconds, but I just want to say a few words like what is this telling us about? What is Bell's theorem telling us about the world? Because it certainly is telling us something, but I don't think it's telling us anything about this weird stuff. Well, what is it telling us? Well, Dennis Sharma was my PhD supervisor. He was a very keen proponent of Mach's principle, that, you know, what determines the inertial effects when you rotate a bucket or whatever, spin round, is all the mass of the universe out there, okay? And by the way, that was very much a motivational idea for Einstein in forming GR. My co-supervisor, mentor at Oxford, Roger Penrose, was very enthusiastic for some years about spin networks. So the spin properties of an electron or photon or something were actually linked to a very large network of sort of combinatoric geometric network called a spin network. I've long been a proponent of one of the ideas which would be consistent with this discretized Hilbert space, is if the universe was some kind of dynamical system evolving precisely on a kind of fractal attractor. And there's links there to non-computability, which is something Roger has been also very involved with, but I'm going to pass over that. The point, the take-home message is that all these things are suggesting the laws of physics are holistic. So this is where it departs from classicality. So the large-scale structure of the universe is not simply an emergent feature of microscopic scale laws. Both large and small scales are direct consequences of this holistic theory. And in my view, trying to probe smaller and smaller spatial scales with yet more energetic and expensive particle accelerators in the hope of finding a theory of everything might be a fruitless exercise. So that, for me, is the take-home message from Bell violation. And it's a bit like zooming into it's like zooming into this Escher drawing with ever more precision and hoping that you'll uncover the meaning of the drawing by so doing. Well, obviously that's not going to be the case. Okay, so what I want to do, I'm happy to have discussion about, we go back to Bell, but I want to kind of give you the second half of this talk, which is to try to ultimately to link this all to some kind of experiment. And this, for me, was an important quote which motivated a lot of my thinking from John Wheeler, who I mentioned to Kaslav I met in my very first ever conference I went to, the first Oxford Quantum Gravity Conference. And it was around, well, that's a bit later he made this quote, but he was always somebody very, trying to reduce things down to kind of basic ideas. And he was always very unhappy with the role the continuum plays in physics. And it wasn't just space-time continuum. He says here about the continuum of standard quantum theory. So the familiar probability function or wave equation of standard quantum theory provide mere continuum idealizations, and by reason of this circumstance conceal the information-theoretic source from which they derive. Okay, now I'm going to skip through a few slides, which I think you will not, all I can do is to sort of say, I want to just give you a flavor. I can't in the time kind of fully kind of give you all the background to this. So just bear with me. And when you do this rationalization, what you discover is that you can represent the individual Hilbert vectors in one of these rational bases by a string of bits, if you like, and it's convenient to label the bits 1 and -1. And for one qubit, if you remember with the block sphere or something, you have 2 degrees of freedom. The 2 degrees of freedom in this bit string representation is the fraction of 1 bit, and that's the cosine squared theta over 2, And the phase angle is actually linked to a cyclic permutation. The next slide will give you some sort of very vague flavor of what I'm trying to say here. But the complex phase in quantum mechanics is linked to a cyclic permutation of those bits. Now, there's an overall psi here, which is a generic permutation, which corresponds to the global phase in quantum mechanics, which we ignore, but it turns out to be important in this model. Just to say about, again, this would take like too long to go through properly, but complex numbers are represented by, if you like, operators on these bit strings. They're just permutation negation operators. So this I, which is two block matrices of L over 2, where J is itself a block matrix with off-diagonal terms, that has a kind of complex structure. So if you operate it on a bit string with I twice, you'll just get the negation of the bit string. So it has a kind of complex number structure, and you know, if you operate on it, it can be represented by a cyclic permutation. Zeta is just a cyclic permutation by 1. I'm going to just flip over this because it'll take too long to go into this. Two qubits in this model would be represented by 2 bit strings. And in quantum mechanics, 2 qubits have 6 degrees of freedom. The 6 degrees of freedom can be represented like this, and you can go upwards 3 length L bit strings in quantum mechanics. There are 14 degrees of freedom. That's represented by those 3 bit strings. And you can carry on building up, building up, building up. But perhaps you can see there'll be a problem eventually, because if the bit strings have a finite length, you eventually run out of bits. You know, each added bit string increases the number of degrees of freedom exponentially, but you're going to eventually run out of the ability to keep increasing the number of degrees of freedom exponentially by the length of the bit string. So in this model of discretized Hilbert space, this notion of what I call qubit information capacity becomes particularly relevant. And I would just again say, in quantum mechanics, the quantum mechanical limit is L equals infinity. So in quantum mechanics, everything I'm talking about would be infinite and there would be no problem. But when L is finite, there is a problem. So the problem is that the information in n qubits is growing linearly with n, but the Hilbert space dimension is growing exponentially with n. So sooner or later, there's going to become a kind of collision of these two. One, you know, the two can't coexist peaceably forever. And in particular, when n, the number of qubits, exceeds this log to base 2 of L, then there isn't going to be enough information, there aren't going to be enough bits in those bit strings to allocate even 1 bit of information to each Hilbert space dimension. And when this occurs, in this theory, okay, it's all predicated on this theory, of course, being correct, which it may not be, but if this theory is correct, this is the point where quantum mechanics will have failed. So then a crucial question becomes, what is the value of L? What is L? You know, if I'm claiming it's finite, I need some way of fixing it. And that's where I want to kind of talk in the last few minutes about the last part of the talk about how this links to the measurement problem in quantum mechanics. And in a way, state reduction or the quantum state collapse is whoops, sorry, going forwards. Is linked to a reduction in this qubit information capacity until the classical limit, L equals 1, is reached. And this is where I want to bring in these p-adic numbers again. So this is a Cantor set, and at different levels of iteration. So you start with a unit line, you throw away the middle third. In the first iteration, you throw away the middle third of those 2 bits, and then you throw away the middle third of each of the 4 bits, and then you throw away the middle third of each of the 8 bits, and so on and so forth. Now, you can use these p-adic numbers to label, this is the whole point, that you can label these bits. So 0 and 1, 0, 0, 1, 0, 0, 1, 1, 1. The point is you can add, multiply, divide, and the corresponding sum or multiplicand corresponds to a point in the Cantor set. So in this model, state reduction, so if you remember, I'm representing a bit by a bit string. For the sake of argument, we'll just say L equals 4 here. So take that point S. There are 4 bits, which I'll call 1, 0, 1, 0. What I'm going to do is steadily reduce the information content, essentially by shifting everything to the right, which corresponds to a division by a half, and then just forgetting about the fractional part. So 1, 0, 1, 0 goes to 1, 0, 1, goes to 1, 0, goes to 1. That's the state reduction step. But look at the point next to it, which is 0, 0, 1, 0. That goes to 0, 0, 1, which goes to 0, 0, which goes to 0. So you've got a natural, this process of loss of information corresponds to a natural instability. And of course, instability is exactly how measurement is seen in some of these models. I mean, Everett thinks of it as branching. In this case, it's more of an exponential divergence of trajectories. And Roger, in his, for example, in his Road to Reality, has this. He talks about the Penrose, talks about the Hawking box, where he thinks on the right-hand side of these diverging trajectories as corresponding to situations where state reduction occurs. I'm skipping over this a little bit quickly because I'm running out of time, but the point is I have a model for state reduction, and what I'm going to do now is introduce gravity by assuming each step takes exactly 1 Planck time. So I have a reduction time of L minus 1 steps times the Planck time, and what I'm going to do now is equate that to the Dioschi-Penrose collapse time, and that gives me a value for L, which is the ratio of the Planck energy divided by the Dioschi-Penrose E sub g, which is this gravitational self-energy. So when Eg equals or is greater than Ep, this, by the way, this curly thing, or this hooked thing, is what's called the ceiling function, which just takes you to the nearest integer above that ratio. So when Eg exceeds Ep, you get L equals 1, which is my classical limit. If you put Eg identically equal to 0, you'd get the infinity of quantum mechanics. But in general, you'll get some finite number. And this is where I'm skipping over a lot of kind of calculations, but I've looked at estimating E sub g for typical qubits in a quantum computer, and there are various formulae that you can use, and this is where you end up with numbers around, like, depends on what type of qubit one's talking about, but numbers around 2 to the 200 to 2 to the 400, and certainly less than 2 to the 1000. So this is where we get an experimental test of this discretized Hilbert space, because it basically says if you have a quantum algorithm that uses, well, certainly more than 1,000 qubits, then the quantum advantage will saturate, because you run out of information in Hilbert space. So if you need 1,000, if you're using the Hilbert space of 1,000 qubits, if that's what you really need to get your quantum advantage, then I'm sorry, but if this theory is correct, you won't get that quantum advantage, because you will run out of bits. Hilbert space will sort of saturate at that level. So I've seen papers claiming that, in a few years we'll be able to factor 2,000-bit RSA integers. Well, my claim is to do that you need 2,000 qubits, fault-free, noise-free. Well, okay, in practice they'll use 1 million noisy qubits, but in a way that doesn't matter. The argument is that you'll never be able to factor. You'll run out of information to factor such a big number. It doesn't matter where Elon Musk has said we could place quantum computers on a deep crater on the dark side of the moon. It won't make any difference, because you can't shield the world from gravitational effects. Okay, so I've pretty much finished, actually. So we can go back to talking. If you, there's a paper which is still in review, but it's on the archive, testing quantum mechanics with quantum computers. And I'm sort of putting the finishing touches to the earlier bit on Bell's theorem, which will be posted hopefully on QuantPH, but we'll go into a special issue of the Institute of Physics in memory of Basil Hiley, who I knew quite well, who was one of David Bohm's collaborators. Okay, so what I'm claiming then is that von Neumann's axiom that quantum states belong to the continuum vector space H is too liberal, and that's what makes quantum mechanics incomprehensible. I presented, well, maybe not, 3 compelling reasons for discretising H. Gives you a very explicit representations of the information-theoretic content of the wavefunction in terms of those bit strings. I would say it provides new conceptual understanding of the violation of Bell inequalities, because it doesn't require one to abandon realism. It doesn't require one to adopt some kind of weird non-local universe. It doesn't require you to give up on free will or any of the other sort of stuff, but there is a notion of holism here. But it basically comes from the violation of the measurement independence assumption, not for the nominal settings, but for these exact settings. And of course, you're not testing that when you do a classical experiment with tossing a coin. You're not testing that aspect of Hilbert space. You're not. I mean, Bell's theorem is something. Just to answer Kozlov, I think your point. Bell's theorem is something which, like the complementarity experiment I did with the Mark Zender, or something I didn't talk about in the non-commutativity of observables, which also makes use of that impossible triangle. The structure of that experiment forces you into considering these counterfactuals which lie in the gaps in Hilbert space and correspond to those irrational settings. When you just do an ordinary classical experiment, the counterfactuals don't force you into thinking only about those gaps. The counterfactuals are also kind of smeared out in the sense that they can be satisfied by rational states. They don't force you into considering the irrational only, whereas these experiments do. And I'm claiming that there is a novel solution to the measurement problem, singular limit, quantum mechanics is L of infinity, and perhaps the most useful application of quantum computers, if they can't encrypt RSA integers, maybe their most useful application will be testing the breakdown of quantum mechanics. Thank you. Just want to get a glass of water. Thank you.
Hello, thanks for the nice talk. I wonder in the part of the Bell inequalities, because you mentioned that you're not like excluding free will in the sense, I would pose it rather than free will, saying that you are not forcing that there exists an extra mechanism that forces it could be the choice of the scientist could be determined by whatever does not belong to the theory, right? Okay, because you're only taking the nominal. But my question is, finally, the setting that is conditioning what the outcome is gonna come. Of course, it cannot be fully determined by the scientists because it depends on arbitrary on some other stuff. But my question is this possibility of violating Bell inequalities tacitly asking something about that, about this noise that would how this noise that would shift would make a difference between the nominal choice and the actual choice, how this noise should behave? Is it saying something tacitly about how the gravitational wave that is passing through and it's shifting? Because if it is so, then how is this distinguished from this sort of super deterministic approaches that would be, or whether it is the case that this thing that is passing through and is shifting, it's making a difference between the nominal and the actual measurement setting, whether it would have some non-local properties, or what is the, because I feel that it should have one of the other two of these two properties, right? If I'm not wrong.
Yeah, I think perhaps where the way you're thinking about this, I mean, I can understand it, is you're thinking of this these rational number constraints as some kind of imposition somehow on the world, and and without these, they would all just be these, what we traditionally think in physics as kind of irrational, the irrational sea of numbers, and that's not, in a way, that's what I'm trying to kind of get away from, and that's why I had a couple of slides, talking about the fact there is a different way to think about rational numbers. So don't think of these gravity, something. There's something kind of like almost super deterministic. This is your point, I think, that is kind of fixing those gravitational waves to have this rational, to have these rational things. And no, I don't think that is the way to think about it. I think just to think of the rationals as sort of being all there is. There are no irrationals out there, and there is no special, like, super deterministic constraint which is forcing them to be rational when they really want to be irrational. No, that's not the right way to think about it, I don't think. Whereas, yes, I would say, I mean, who knows what free will really, really, really is, but in a sense, I'm saying it kind of doesn't matter. So just go back to the Mark-Sender, because that's the easiest one. The experimenter can choose to do the which way or the interferometric experiment as they like. I mean, whatever determines that, I don't care. They do something. All I'm saying is once they've chosen one, the other, which would now be counterfactual, necessarily will violate this rational constraint. It'll force it to be an undefined number. I mean, in the old days, let's say we call it an irrational number. I just would say it's undefined. So I think there is something robust here that's not dependent on some extremely finely tuned structure, but you have to kind of get rid of irrational numbers in your head to see that, I think.
Can I follow up on that?
Yeah.
And I give them to you. I thought, at least in a bell, I mean, I also see this kind of dichotomy here about story about the bell and the story about Hilbert space. But in a bell, I thought that you want to say that even if we want, like, to choose arbitrary setting, we can't, because they are only rationals.
We can choose. No, I'm not saying that. We can choose as we like. I mean, whatever.
But eventually we will choose only rationals.
Yeah, but you say only rational. This is the point I'm trying to make.
Don't
Don't say that.
It's not my question.
Don't say that. Don't say only rational. That's all there is to choose.
Only what
there are lots of rational numbers out there. There's a countable infinity.
But then I thought that this, at least in the bell, is a property of, let's say, device. Okay, there are only rationals there anyway. Now I'm coming back to my question. Okay, let's take two balls. I take now a circle or ball that have like full real numbers, I mean ideal mathematically, and then I ask myself, if I correlate now balls around us, and then I choose, I don't know, this direction of the ball, that direction of a ball, I try to mimic Bell experiments I can make with the balls. I fail to violate. But still, there are only rationals, especially my precision with which I can go with the precision in which I want to think like orientation. I can have some axis on a ball, and so with which precision I can go along that. I can, from the point of view of precision of making settings as precise as I can even go beyond what I can ever achieve in quantum mechanics, and nevertheless I will not violate. So what is this?
Well, it comes from the specific requirement that these correlations are described by the scalar product A dot B. I mean, you know,
you want to have an explanation for, I thought, partially for quantum theory, and now you're putting on a back thought again.
Well, I'm just saying there's something about quantum mechanics that is forcing you in the Bell inequality is forcing you to there's something about the nature of quantum physics that in the Bell inequality is forcing you to deduce or realize that the counterfactual worlds are constrained to have these where the relative angles have these rational cosines. So if it was a classical theory, you might have this spherical triangle, but you would have some other property, let's say, where you could certainly satisfy it for all three sides of the triangle. You see, it comes from the fact that it's the what you can't do is the cosine of the relative angle has to be rational. I mean, for the angle, if it was the angles themselves,
introduce cosine as many. I mean, what I want to say, it's not rational constraint is then not explanation for me because it doesn't work always. By experiment,
it's the question of the question is because in classical physics we do. I mean, we typically embrace counterfactuals all the time because we're always asking, what if we had done something, we hadn't done something else? And there's nothing in classical physics that would typically say, no, you can't, that's not an allowed counterfactual. You know, that never happens. Yeah. We're allowed to, you know, if we throw a ball from A to B, we can imagine throwing the ball with half the speed or a quarter of the speed. And the classical laws of physics give us perfectly good trajectories for the ball. So
the question is for me, what do you want to assume and what do you want to prove? Because I can define classical by not violating Bell inequality. And I'm now asking, what's the reason we don't? And I thought you want to provide us with rational, but then
it's the gaps. It's the fact that what I'm exploiting, which I don't think classical physics exploits, is that there are gaps. If you have a discretized system, because you can obviously discretize things in classical physics as well, but there's something peculiar about Bell's theorem and the complementarity result I talked about, which exploits the fact that there are gaps in between the rationals, where these states are undefined. It forces you to consider counterfactuals in these gaps. And that's where you can explain the violation of Bell inequalities and all the other quantum properties without recourse to the weird stuff that I talked about. That's what I'm trying to say.
So I have a question about the way you computed the number of degrees of freedom in your theory and in quantum mechanics, because I mean you're not speaking about continuous degrees of freedom because nothing is continuous, right?
That's correct.
So what are you counting? What do you call a degree of freedom in your theory?
Yeah. So if you take the single qubit in quantum mechanics, you know, you're represented by a point on the Bloch sphere with two degrees of freedom, and you should correctly say that in quantum mechanics these are continuum degrees of freedom. Yes. What I'm saying is I have 2 degrees of freedom which are not continuum, but they vary over something like 10 to the 100, you know, values. So for all practical purposes, you can think of them as continuous.
Okay.
It's only when you start to get Hilbert spaces with the size of 10 to the 100, which is not that big in a way, then you start to feel the granularity, and then quantum mechanics breaks down. But that's the point.
Okay, if your theory allows you to define, and I guess it does, no, separable states, no, then well, like, I don't know, depends on what you call a degree of freedom. You're comparing this with a quantum case, right? I mean, in order to make the case that you...
Well, if I have theta, you know, theta is theta is a latitude or something. I mean, it varies from 0 at the North Pole to pi at the South Pole. I mean, that's a continuous degree of freedom in quantum mechanics, and I'm saying I'm replacing that with 10 to the 100 latitude, lines of latitude. Well, that's, in any practical experimental sense, if that's all you're testing, that single thing, you could never, ever, ever, ever produce an experiment which could distinguish between two things which are 10 to the 100 radians apart. It's just unbelievably small. So for all practical purposes, that's a continuum.
But then what I don't understand is how come that, well, if you I don't know, if you take them now continuous, and I don't really understand how if your theory is supposed to approximate the quantum physics, I don't understand why you lose the degrees of freedom. I don't understand why you don't get an exponential.
You don't understand why I don't get.
You don't get exponentially many degrees of freedom. Well,
I do get exponentially many. I do get exponentially many degrees.
Linear in the number of qubits, no?
The amount of information is linear in the amount of qubits, but the degrees of freedom.
What do you mean information?
Sorry?
You say the amount of information. What do you mean by information?
Yeah, well, that's this. I'm saying that you can represent the qubit state in this discretized Hilbert space by a bit string of length L. That's what emerges from the analysis.
Then
so
the way that you're counting information, then it's infinite information in a quantum system, no? And even a qubit, right? Because
say again?
Then there's an infinite information in a
There's not infinite information, no. There would be infinite if it was a continuum. It's in the continuum limit.
That's what I'm saying, right? I mean, but I don't understand why, you just made a comparison and then you put something linear versus something exponential in the standard quantum mechanics. I think you're not comparing the same thing.
I'm not comparing the same thing, you're right. I'm saying that the degrees of freedom, well, you shake your head, but I'm trying to give you an experimentally testable test of this notion of discrete Hilbert space. And what I'm saying is that once you discretize Hilbert space, you can't support an indefinitely large dimension with indefinitely large number of qubits. And it's because the linear increase in information eventually conflicts with the exponential growth of Hilbert space. That's the idea.
I just have problems with the definitions of dimensional information that I think that you're.
Well, I tried to describe it. I mean, I have these length L bit strings. I can have n of them. Yeah. I can support the exponential increasing number of degrees of freedom as long as the L is sufficiently big. So if L was infinite, I could have as many infinitely growing degrees of freedom as I like. Well, this is the thing. I mean, this is just a combinatorics. This is just combinatoric mathematics. Just to write down n of these bit strings and ask how many degrees of freedom can I represent. I mean, there'll be granular degrees of freedom, but the granularity is determined by the length of the bit string. This is just combinatoric mathematics.
But so this is not making any sound. It's just for the. Okay. Okay. So I really like the talk. I didn't know these ideas. I want to make some general comment just to see a bit. So, okay, let me say the following, that I don't pretend to have understood all the details here of your work. I am personally very sympathetic to the idea that, let's say the world is emergent from an underlying combinatorial something like spin networks and so on. And personally, I always thought that it cannot make sense that we have continuum probabilities. There must be some sort of discreteness. I don't think physics makes sense in the continuum, in a limit, and so on. There isn't anything infinite. So I find all the ideas you presented like a coherent package of how this could come about, right? How is discreteness gonna come in quantum mechanics, and it will certainly change quantum mechanics. Now, the striking thing, as you've emphasized, is that you're saying this is phenomenologically relevant and testable, and maybe soon. And so there is something that is making the numbers work, some big magnification. So this is a part that I didn't really get. You didn't have a lot of time. You went fast through it. So there is something about assuming time to be discrete at the Planck scale. That's how you bring in constants. But then there is something else, some other assumption that I didn't get, which is the relation with whatever is being assumed in the Penrose-Diozzi model. And I just wanted to understand how dependent is the feasibility of this on the Penrose-Diozzi model working, or on the details of this and so on.
Yeah. I mean, for a long time, I had got as far as saying, look, I have all these things in place, but I just don't know what the value of L is. Is it, 10? Is it a trillion? Is it 10 to the trillion? Is it a Google? Is it a Googleplex? What is it? And the crucial step was to say, well, if I can develop a notion of what is going on during the measurement process in terms of L, if I can link a kind of state collapse time to L somehow, then we have a model, the Diozzi-Penrose model. If I can relate the two time scales, then this will give me a value for L, because I'll have a time scale yeah. I mean, that's my time scale, L minus 1 times a Planck time. This is my way of bringing in gravity. There are L of these steps, which is this fractal sort of zoom. It's a magnification into the fractal till it stops at the larger scale. But that still doesn't tell me what L is. But Diozzi-Penrose says that the collapse time is h bar over E sub g. So if I just link that, just equal Diozzi-Penrose to my Tor star, then that gives me that formula, which is a way of calculating L. So my subsequent claim that you won't be able to factor 2000-bit integers is based on this calculation. So it kind of appeals to me because I like the idea. We think in quantum gravity as it's gravity which kind of eventually banishes the space-time continuum, and we get discretisation in space-time. Well, this is a kind of an equivalent idea that gravity is ultimately the thing which banishes the continuum from Hilbert space.
Right, but all right, but let me see.
This is an assumption. I mean, it's not you can believe it or not believe it. I mean, the assumption is L is set by gravity. So this is an important point, by the way, that my claim for the 2000-bit integer being unable to be factorized has nothing to do with collapse as such. It's nothing to do with collapse. It's just that I'm using the collapse model to get a value of L. Once I've got the value of L, forget about collapse, because this has got nothing to do with collapse. It's just a statement about running out of information to do your factorization of your big integer.
Yes, independently, if L is of that value, then you will still have that. But in order to derive L from that, you are relying on the fact that the Diozzi-Penrose time scale is much larger than the Planck time, right? That's where you get the big number.
No, the Diozzi-Penrose time can be. Oh, so you say longer than the Planck time? Yes, longer than the Planck time. That's correct.
How you get the big number.
Yeah, it can be longer than the age of the universe. I mean, for these qubits, the collapse time is likely longer than the age of the universe. So the collapse has got nothing to do with the constraint on the quantum computing. It's just to get the value of L. Maybe there are other ways of doing it, but I don't see that.
Yeah, I would also kind of, I have a little bit more reservation towards that, because for Diozzi and Penrose, you could be a 1 degree of freedom, a center of motion of a big object that is replaced on different places. It has nothing to do with the complexity of the Hilbert space. It's just
no, yeah.
And so that reason for collapse and your reason, which is more like doing quantum computation, being able to address every possible state in a complex, are completely different. So
completely different stories. Completely different stories. Completely different stories. It's just it gives me a way of calculating L. That's the only point.
Okay. So very last question, and then we finish, please. Yeah.
Thanks. No, it's just a very straightforward question. Like when you showed initially the Mach-Zehnder example, okay, you were confronting the two states into different bases.
Yeah.
Okay, but usually in standard quantum mechanics, that change of basis is made by a unitary.
Yeah.
Okay, a unitary transformation.
Right.
And the fact is that that unitary in a continuum in space is defined as a continuum unitary with continuous variables.
Correct.
Okay, and now my question is, if we would start, if we started with from a discretized Hilbert space, okay, as our field, not field meaning, but okay, where are we playing? Shouldn't we define unitaries which are not continuum? And so, my question is, if we use a continuum unitary to go from linear polarization to circular polarization, it's obvious that if we start from a discrete number in the first, then we will get something strange.
Yeah.
But I would expect that if we define a discretized unitary, these problems wouldn't arise. You get my point? Like either you build a completely discretized Hilbert space with, and this is actually the first question. The second one, which probably is related. No, I'll just drop it because the discretization you are referring to is on the coordinates of this Hilbert space, or on the physical parameters, because there you were speaking about the probabilities and the phase, which are two physical things. But
well, you see, this is always the issue in quantum foundations, that we always end up saying, well, but the world is actually contextual. We have this idea that we can't. We can't really describe the world in much as we might say ideally like to in a non-contextual way. And this is what I think. This is what ultimately this message is telling us. You'd like to say, oh yeah, the Schrödinger equation, it's all kind of basis free, a little bit like GR. It's coordinate independent. Must be right because GR is coordinate independent. Schrödinger equation is coordinate independent, and it's just we tack on the coordinates at the end, because of the basis that we choose to measure things with. But I think what this is telling us is that actually is the wrong way to think about physics, and the bases are integral to the evolution equation. They're not sort of some extra thing that you kind of apply later on in your calculation. I mean, it may well be for all practical, for practical quantum mechanics. It's like in number theory. I mean, there's lots of very interesting and important mathematics where you treat numbers, prime integers as what's it called, analytic number theory, where you just treat them as a continuous field, because you can get lots of interesting properties of prime numbers and things by treating them as continuous. But at the end of the day, prime numbers are discrete, and you'll get mistakes if you assume everything is just looking at the asymptotic theory. And this is similar. I think that lots of obviously important maths, but the point is that the coordinates. I think this is where we've got to get our head. Well, this is my view anyway. Get your head out of this idea that the coordinates is just something you tack on at the end to essentially a coordinate-free theory, and that the coordinates, in other words, the bases, really are playing a central role in this whole kind of axiomatic framework.
Okay, let's stop at that moment. Thank you very much, Tim. About the coloring of the sphere with the rationals.
Yes, and